Hello, and welcome to If at First You Don't Succeed, Norway's two contact tracing apps. I'm Eivind Arvesen. I currently work as Group Cybersecurity Manager at Sector Alarm, which is one of Europe's leading providers of monitored home security solutions. In this talk, however, I'm not representing my employer, so this is an independent talk. First off, a little bit of background. As we're all aware, last year, the novel coronavirus spread all around the world, resulting in a global pandemic. And in trying to contain that pandemic, public health officials perform what's known as contact tracing, which is basically interviewing those that are diagnosed with the disease, COVID-19 in this case, and trying to figure out who they've been in contact with during their infectious period, to get those contacts to isolate and get tested. Now, this process can take a lot of time and manpower, which led a lot of people to start thinking, well, we have sensing supercomputers in our pockets most of the time, so maybe we could automate at least part of the process. And that led many nations soon thereafter to be able to say there's an app for that. So Norway was one of the first European countries that launched a contact tracing app back in 2020. These are basically the defining features of that first app. It used Bluetooth and location data. It had a centralized storage model. It was closed source software. It had multiple purposes, so it did not only contact tracing, but more, which I'll get back to later. And it required registration and de facto identification of its users. There were multiple known issues with the app, including the fact that it used a static device-specific identifier. So a source code repository was accidentally made public online, and thus the media were able to reveal to us that work had started in secret on a digital contact tracing app for Norway. And we were soon able to read about some controversial design choices, including the characteristics I've mentioned already, but also the fact that the app would be producing long-term anonymized and aggregated data, which is risky because often when people talk about anonymized data, what they really mean is de-identified or pseudonymized data, meaning it might be possible to re-identify data subjects in the data set. Now, for a rough timeline of events, the app was publicly highly criticized from the get-go. And in an unprecedented herding of cats, so to speak, over 300 tech professionals launched a petition to change approach. The government, after all of this, and after general cries for transparency, as sort of a democratic proxy, appointed an expert group, of which I was a part of. So we were able to look at all the source code, talk to key players, view all the documentation, and so on. So we were tasked with evaluating the app, and we produced a final public report in which we concluded that neither security nor privacy was handled responsibly. Now, the supplier/creator of the app handled any and all criticism by way of public attacks, which was interesting. And at launch, there was a lot of negative user feedback about things like battery drainage, the inability to register because the backend services weren't scaling to handle the amount of traffic they were seeing. In addition to limited notification support at launch, by which I mean they launched the application for the entire country and started collecting data, but they were really only performing contact tracing digitally for a select few test municipalities. So our parliament then said basically that we'd need explicit consent for each purpose, right, for the application. And then Amnesty International famously stated that our app was among the most dangerous contact tracing apps for privacy in the world, which gained a lot of international media attention. And then the Norwegian Data Protection Authority, after some investigation, declared data processing of data from this app forbidden. Now, a couple of months later, or a short amount of time later, the Institute of Public Health announced that a new app would be made using the Google Apple Exposure Notification Framework. The second app would use Bluetooth only, have a decentralized storage model, be open source software, and have only a single purpose, which would be contact tracing. Now, this time, as mentioned, it would be open source code, and they accepted external contributions. They appointed an external council as community representatives, and they actually invited some of the most vocal critics of the first app. There was an open Slack for feedback and technical discussions and stuff like that. So some of the more outspoken critics of the first app made a point of speaking out and vouching for the new application. And the government ran large-scale ad campaigns, including targeted campaign toward non-native speakers and vulnerable populations. Now, at this time, the launch this time around gained more positive user feedback. Now, as for comparing these two applications, the major differences here are mostly sensors used. So in the case of the first app, it used Bluetooth and GPS, whereas the second app only used Bluetooth data. Purpose for processing in case of the first app was contact tracing, as well as using the same data to evaluate government restrictions. So for instance, they'd analyze public movement patterns. Additionally, after 30 days, the data would go through some sort of anonymization and aggregation process, resulting in data for long-term use and storage for some unspecified research in the future. While the second app, its only purpose was contact tracing. Now, the first application collected a lot of different data, whereas the second application collected only contacts, and by which I mean anonymous identifiers via Bluetooth. The first app stored its data in a central data store in a public cloud solution, whereas the second application mostly stored its data on user's device, that is, until they might be diagnosed with COVID and thus uploaded their keys from their infectious periods, if they so chose. Now, some have argued that even if you look at contact tracing in isolation, to be able to perform that back then, i.e. early 2020 or April 2020 to be specific, you'd still have to collect location data and store and analyze data centrally in order to effectively perform contact tracing. That would be because of platform limitations at that time. And those limitations were mainly that both of the most popular smartphone operating systems, i.e. Android and iOS, had aggressive limiting of background process use of Bluetooth. So for instance, on iOS, on regular applications in the background, you can reliably do Bluetooth scanning. And additionally, if you were to lock the screen, you couldn't, in a regular application, do Bluetooth scanning at all. So it's interesting then to note that Singapore, even earlier than the Norwegian app, early 2020, were able actually to make sort of a creative workaround around those limitations without compromising on privacy. So what they did is they communicated to their users that they would have to try to keep the application active as much as possible. And instead of locking their screens, they'd have to turn their smartphones upside down, which would enable a sort of custom implemented energy saving mode that would dim the screen and so on to save battery, while still being able to do Bluetooth scanning. And it's also interesting to note that while various other countries had various other approaches in the beginning, pretty soon most of them tend to converge towards a decentralized approach using only Bluetooth data. And this can also be seen in the common European guidelines, the EU Commission's recommendations on apps for contact tracing, the EU resolution on coordinated work against COVID-19, as well as guidelines from the European Data Protection Board. And all of these were published before the first Norwegian app was made available. And those requirements and characteristics can also be seen in the Open Decentralized Anonymous Contact Tracing Protocol known as DP3T, which in practice laid a lot of the groundwork for the Google and Apple exposure notification framework, which would come later. Another interesting thing to consider is the way that the different application did key scheduling and identification. So this is how the Google and Apple exposure notification framework handled identifying keys. So as you can see here on top of the diagram, a randomized key called temporary exposure key is created every 24 hours. And these are stored on the user device for 14 days, which is the time in which one presumes that a person with COVID-19 is infectious, so that if they're diagnosed, they're able to upload past identifying keys so that the other user may see if they've come across these keys. These temporary exposure keys then generate a rolling proximity identifier, or RPI key, in the middle of this diagram, which is then encrypted and then used to generate a new identifier every 15 minutes that's sent to other devices for contact tracing purposes. And that would be the rolling proximity identifier at the bottom of this diagram. Now, all of this makes it harder to track users because of how frequently keys change and because some keys expire and so on. Now, it doesn't make it impossible to identify a person, but it makes it much more difficult to do, and it limits what an attacker with much computational power is able to do. Whereas this is a corresponding diagram of the first application's key scheduling and identification that I've made. And while there's a certain elegance to its simplicity, it has some obvious issues. So any one device would always identify itself with the same constant piece of information. Not only is this a new vector for tracking and identifying and potentially impersonating a user of the system, but it also totally undermines operating system level privacy preserving mechanisms that have been in place for years already, such as MAC address randomization for various radio interfaces like Wi-Fi and Bluetooth. So as for known risks in the applications, none of the applications allow users to specify exceptions to data they want to share if they're diagnosed. Now, I've seen that discussed in DP3T. I haven't seen anyone actually implement that functionality, though. And as mentioned in the comparison table earlier, the basis for processing in the case of the first Norwegian app was a piece of special regulation. So it's still not mandatory, but the regulation laid down some limitations, including that police wouldn't be able to access health data nor location data. However, Bluetooth-based contact data isn't necessarily either of those. So it's really an open question whether health authorities might be able to get a hold of that data. And as we've seen in several countries during this past year, law enforcement agencies might be interested in that sort of data. Maybe they want to know who were at a specific demonstration. Maybe they want to build social graphs of those people to see who of them know each other and so on. And of course, the central data storage model here enables data theft, leak, misuse, and function creep really in a way that decentralized storage just doesn't. And it sort of highlights that you can't abuse or lose data that you don't have, which is one of the reasons data minimization is so important. And there's also the fact that users are de facto identified in this first app because they had to register with their phone number to be able to use it. And in Norway, you're not practically able to get a phone number without identifying yourself because of regulatory requirements and so on. Not to mention the fact that phone numbers are actually considered public information. So there are free and publicly available lookup services where you can search by name or number, except for people who have explicitly opted out of that, which aren't that many. The app was found to communicate a lot of potentially fingerprintable analytics, like operating system version, hardware manufacturer, carrier, screen resolution, that sort of stuff. And while any one of those attributes might not be unique enough to identify any given user, in combination, they might be. And in particular, if you combine that with other data sources, it might be. The data from this app wouldn't meet data interoperability standards within the EU, because most other countries were standardizing on decentralized solutions that use only Bluetooth identifiers. The application also used text messaging for exposure notifications, even though text messages are known to be an insecure communications channel, which the Norwegian media demonstrated pretty early on by having a security professional spoof text messages ostensibly from this system and making a big point out of that. If users were to trigger deletion of their data in the central solution, that would also trigger audit log deletion for some reason. There were general quality issues in the contact analysis code itself, and the anonymization process for the long-term research data mentioned earlier was never completed before the app was shut down, which is odd because the app was running for more than a month. And there was a general lack of transparency in that the source code was closed. The purpose of data collection and data use wasn't really communicated that clearly. Of course, in the case of the Google and Apple exposure notification framework and the second app, there's a risk in that we're basically trusting Google and Apple not to do anything else than what they claim to be doing, and that they won't somehow exfiltrate the locally stored data. As for vulnerabilities, the first app is obviously trivially vulnerable to identification, tracking, and impersonation of users, as well as most other known vulnerabilities in other apps, actually, including those you can see on the right side of the screen here. So Google and Apple's exposure notification framework, and then the second app, is still, it's not perfect. So it's still susceptible to attacks like third-party correlation attacks, replay attacks, cross-correlated mapping attacks, and so on. And there's also a concrete risk in that Google and Apple don't inspect the backends of public health providers. So in this case, you have to, when you're diagnosed and you want to upload your data, you're connecting to a publicly or a government-owned service where you identify yourself in order to validate that you have a diagnosis, which gives you a token that you're able to use to upload your data in another system. Now, you can't be traced by the token, but the government or the health authorities own both systems involved. So if they were to log, say, your IP address and the date time at your access to both systems, they would be able to correlate and thus identify any diagnosed and uploading user. So in concluding here, I'm no lawyer, but if we are to look at the principles laid forth by the GDPR, it seems to me that the first application has a huge mismatch with the GDPR's 7 key principles here. And in fact, I think this meme just about sums up my feelings for the first Norwegian app. So in conclusion, we should strive for preparedness, I think, as to not be in this position again. So you don't want to be in a position of solving difficult, novel problems in a crisis using tools that weren't built with that purpose in mind. And you obviously also want to involve privacy and security experts in developing high-risk engineering solutions. Good technology respects its users as well as their interests and rights, I think. Even a major pandemic is not necessarily a reason to lower privacy standards, because you can do it with privacy by design, right? Additionally, we need to work towards objective rules and metrics and cement privacy engineering as an established field with agreed upon principles, and to make that part of general software engineering knowledge. With that, I'd like to say thanks for listening to my talk. Here's my email address and a Twitter handle if anyone wants to reach out. You can also find a few blog posts about the first app on my website, linked there. I look forward to your questions, and thanks again.